All right, good afternoon. Okay, let's see. Next week is spring break. Don't show up, there won't be any lectures. So that's an opportunity to catch up a little bit on the project, maybe, if you're not gone skiing or whatever. Let's see. Any questions on the project? Anybody has kind of started already on it? Anybody started thinking about it? Okay, a little bit. Good. What I'm going to do, I'm just going to give you some extra information at the beginning of this lecture. Just for the rest, I think there's very little practical administrative stuff to be told. It's fairly quiet. As I said, I want to make sure you get the maximal time to work on the project. So I'm just going to introduce some other concepts that you should be aware of, and it could be useful when you're executing the project. In the first one is something which I call the CSD notation, okay, which might become important or useful once you basically start executing the project and start doing the optimization. First of all, who's familiar with two's complement notation? Anybody ever heard about two's complement notation? Who has never heard about two's complement notation? It's okay, good. If you have never heard about it, it's important because it's an important thing for the execution of the project. Question is, obviously when we do processing, filtering, and all this kind of stuff, we work with numbers, right? Binary numbers. And I said in our case, these are going to be, the input numbers are going to be integer numbers of 8 bits. Now, typically numbers can be positive and negative, right? Any signal that you have, a sinusoid or something like that, it goes positive, goes negative. So the bottom line question is, how do you represent negative numbers in a binary notation? It's an important thing to think about. Now, there's different ways of thinking about it. Let's say I have 8 bits. What I could do is say, okay, what I'm going to take is my 8 bits, and I'm going to divide them in 2 chunks. I take 7 bits here and 1 bit extra. And the 7 bits are going to be used to represent my magnitude of my number. Okay? Now, we have 7 bits. What's the maximum number that I can represent? Should be able to figure that out. If I have 7 binary bits, what's the maximum number that I can basically represent in that space? 127. So if I get 1, 1, 1, 1, 1, all ones, that's basically 127. Okay? And then what I could do is use the extra bit that I have here to represent the sign of the information. So a 0 would be a positive number, 127. If I put a 1 here, it says this is negative. Okay? This representation is called sign magnitude representation, SM. Okay? It's fairly straightforward. It's a sign plus the magnitude. But from an implementation perspective, it's not the most desirable one. Because now you can see that you have to do different things. You add 2 numbers together, one positive and negative. You're going to have to do different things with your sign than with the rest of your number. So that's why people have come up with a different way of representing negative numbers. And that's what's called two's complement. So we do the same thing for positive numbers. A positive number is just represented as you always would do. But for a negative number, what we're going to do is we take our magnitude, M, and we invert that. We invert all the bits and add 1. Okay, so if I want to transform a positive negative number into a positive number into a negative one, what you do is invert all the bits and add 1. So let's take a very simple example. If you have the number 1, okay, that's the representation of 1, right? Very straightforward, all zeros and 1, 1. So now the question is, what would minus 1 look like in a two's complement notation? Well, as I said, you do 3 steps. You do 1, 1, you invert all the bits. Okay? and then you add 1 to it. So adding 1 to this number is 1, 1, 1, 1. 8 ones. So and actually in this case, minus 1 is equal to all ones. 0 is all zeros. Plus 1 is 7 zeros and a 1. Okay? And you can keep on repeating that. If you want to figure out now what's the maximum number that I can represent in this representation, from the positive end, obviously if you look at the first bit, we'll tell you what the sign is. Right? All positive numbers will always have a 0. All negative numbers will always start with a 1. So it looks in some sense like sign magnitude, but the rest of the magnitude is not the same, because it's this inverted plus 1 type notation. Okay? So let's take an example. Let's look at the absolute largest positive number I can represent. That's this, right? It has to be a 0 for the positive sign, and then 7 ones, which is going to be equal to 127. Okay? Now, what would be the counter in the negative space? What would minus 127 look like? Well, as we said, we just invert all the bits, and we add 1. So this becomes this. This is equal to minus 127. Actually, it turns out that with this notation, I can not only represent minus 127, but I also can have this number. A 1 and all zeros. If you will now invert it, if you want to go back to positive, you do the same thing. Invert all the bits and add 1. And if you do so, you get 0, 0, 1, 1, 1, 1, 1. You add 1 to that, you get basically 1, 0, 0, 0, 0, 0, 0, which is not a sign bit in this case, it's a positive space, is actually 128. So with 2's complement, I can represent everything from 127 to minus 128 in the representation. So I get actually one extra word that you can represent, which is nice. Now this seems to be complex, but actually the beauty of this is that with 2's complement, I can take negative numbers and add them together to positive numbers, and the result is always going to be positive or negative. You don't have to do anything special for the sign bit or for the sign magnitudes bits. They are all processed in exactly the same way. So from an adder perspective, for instance, I want to add numbers together. I just put a positive number and a negative number. I add them together like we would do with our normal full adders, and you get the result. So it's a very simple way of manipulating both positive and negative number. That's why every computer, almost every computer I know of today, uses 2's complement notation. Okay? So that's an interesting thing to observe. So let me introduce something else. Let me clean out that slide here. Here, I think. Erase. Oh, ink on slide. So now we know how to represent negative and positive numbers. Sometimes, if I want to, as we will see in all filters, and I come back to that in a second, sometimes I don't want to do only addition, but I also would like to do subtraction. It seems to be like a common thing to do, right? You want to have an adder, you want to have subtraction as well. So how would I do subtraction in, or how would I build a subtractor? Right? That's an interesting question to ask, because probably you will see as somewhere in your project you will need something that subtracts. Not in the first phase, but maybe later on. So how would I do that? Subtractions. Would I have to build complete new hardware, or can I basically use a traditional adder and modify it a little bit in such a way that my addition becomes a subtraction? Now, addition or subtraction, if I want to do A minus B, is nothing else than A plus minus B. Right? So what I could do to basically do subtraction is add the negative value of the B input to the overall, to A. Now minus B, if we are in 2's complement notation, we know exactly what it is. Minus B, to get from B to minus B, how do we invert a number from positive to negative? What you have to do is invert all the bits and add 1. Okay? So actually, it turns out I can do this very easily with a full adder. So I have my full adder, 8 bits in, A and B. So I have 8 segments here. And one of the inputs is A. So let me just write it like this. So you have your full adder block, and one of the inputs is A, and that's 8 bits. So that's add. Okay? So what we say, if we want to do a subtraction, what we should do is add minus B, and minus B is B with all the bits flipped, right? So what I can do is I take the B input and I add an inverter on every bit. Adding that inverter for every bit is doing the bit flipping. So we're already a long way towards our subtraction, but there's one thing missing, right? I have to add 1. So one option is to add another adder, to add a 1 to this thing. This kind of seems to be a lot of work for a very little thing. So any idea how I can modify this little circuit here so that with with 0 overhead actually, I can turn this into adding a 1 at the same time as well.
Can you use carry in maybe?
Sorry?
Carry in?
The carry in, that's exactly right. Remember this adder? There's always 3 bits, A, B, carry in. Now for the first bit, the 0, the least ordered bit, we always connect the carry in to 0 because there's nothing coming in from the previous word. But if I now would connect this just to 1, I can turn this into something that subtracts very nicely. So I can use a simple full adder, add inverters of all the second input, and change the carry in to 1 from 0. And you're done. So that's beautiful, right? There's very little overhead. Now I can make, with this extra money, I can now change my adder into something that's a programmable add subtractor. That would be nice, right? You have a block in your hardware and say, okay, sometimes I want to add, sometimes I subtract. How would I do this? Well, A remains the same all the time. Then what I'm going to do here as my just let me do some erasing here. Eraser. Okay. So I add a second input B, but instead of using an inverter here, I'm going to use an XOR, which has B as input or plus minus. And then I use also plus minus as the other input. Plus minus is the choice between doing addition or the subtraction. Okay? When it's an addition, we just set it to 0. When it's an subtraction, we set it to 1. So in that case, you can see that the carry for an addition is going to be 0, the carry in is going to be 1 for the. Turns out also that if you take an XOR, setting an input to 1, if you take an XOR function, 0, 0 becomes equal to 0, 0, 1, or 1, 1 is equal to 0, 0, 1, or 1, 0 is equal to a 1 output. Actually, the next is a programmable inverter. As you can see, if I set the input to 0, I just take the input and feed it to the output. If I set the input to 1, I invert. So this is a programmable inverter. So with this, now I have a programmable subtractor adder circuit. Again, with very little overhead. Okay? Now, why do I insist on talking a little bit about subtraction? You say, oh, gee, my filters, it's only adds and shifts, right? That's all I have to do. Where would subtractors ever come in? Well, here's one more trick I'm going to learn you. That's the last trick for today. Next class, I will show you some more. Step by step, you're getting very proficient in the design of arithmetic circuits. Let me erase this again. Okay. Remember our shifts. Right? It says, how do you do multiplying by a certain coefficient? Right? How do I multiply by 3.75? Okay. Well, the answer is this is equal to 0, 1, and then like this. 0.375 is multiplying by 1/4 and add 1/8 of the signal to it. So we have 2 bits here. That's our coefficient, 1/4, 1/8. Okay? If we basically would say we have somewhere a binary point. Now let's assume, let's go a little bit more generic. Suppose I have something like this. That would be my coefficients. Now remember, for the add shift approach, zeros are cheap, right? You don't have to do anything. Every one is going to cost you an addition. Because every time I have a 1, I have to do a shift and an add. Now I'm cheap, and you know, every designer should be cheap. I try to minimize always the amount of hardware you're going to need. So if I look at this thing and say, boy, that's kind of expensive, right? I have to do 6 additions to implement these things. Wouldn't it be nice if I can maximize the number of zeros? Okay. Now, one way to do that is rewrite your coefficients, maybe round it off somewhere to something which is easier to use. But there's some other tricks. Actually, turns out there's a way for me to minimize the number of ones in this thing so that I never have more than 50% ones in the representation. Right now I have, let's say, if you forget about this thing here, I get 1/2, 1/4. I get out of the 8 bits, I get 6 ones. That's expensive. Wouldn't it be nice if I have maximally 4 ones, and maybe smaller number of them? So there's a very simple trick of doing so, and that is basically changing the number system. You know, number systems, you have decimal, you have binary. There's also something which is called redundant binary. Redundant binary says, well, I'm not going to use 0, 1, but I'm going to use as representation the number system -1, 0, and 1. So I have 3 possible representations at every position. Okay? This is obviously redundant because I could do it with zeros and ones, but I'm going to try to use -1s, and we'll show you how this will help. Because if you look at this sequence here, you say, well, this sequence is what? 7, right? 7, that's not a very, 7 is a nasty number because it has a lot of ones. If I were, but we know that 7 is equal to 8 minus 1. Right? Same thing. So if I now would replace this by a representation, I put a 1 here, 2 zeros and a -1 here, it's the same thing. It's 8 minus 1. Still 7. And I eliminated that sequence of 1s. So any sequence of 1s, it may be infinitely long, can always be replaced by a -1 at the top here, and all zeros, still 1 at the top. It's an equivalent transformation. That's where this canonically signed digit representation, or this redundant representation, works out very nicely. Okay? Now, transforming one number into the other one is non-trivial, because I started here, but now you see that by adding this 1 at the top, this 8, I suddenly have 4 ones in sequence again. Right? I have this one, this one, this one, and this one. I can do the same transformation again. Okay, so while this is equal to, if I again erase a little bit of this stuff here, I can say that this is now equivalent to -1 stays. This I'm not going to do, but here I have 1, 1, 1, 1. So I'm going to replace by -1, 0, 0, 0, 1. And this is exactly the same as the original number. Same value. But as I see, I now use both 1s and -1s. But you can see instead of having 6 1s here, I have only 3 1s in this representation. Means I save 3 adders, which is exactly what I wanted to do. Well, not really adders, because here what I do is, this representation is plus, minus, 2 minus 1, right? It's plus half. Next thing is, well, that's a quarter, that's an 8, 16. I get minus 138. So I'm taking my value A, my other coefficient, my value I take, I multiply it by 1/2, that's shifted over position, and add it. Then I have to take A, shift it over 30 over 5 bits, and subtract it. Instead of addition, we use subtraction. That's why I need a subtractor. And then I have minus 38, 64, 128, minus 156. So a very simple representation of my coefficient. Plus 1/2, minus 138, minus 32, and minus 256. So you can see by some manipulation, on the coefficient, I actually can make my hardware cheaper. Okay. Now, you will see in the project that the numbers I gave you so far have some room for optimization. First round, we're not going to mess around with that. We're just going to take the coefficient as given. If it says 1 half plus 1/4. But later on, the second phase of the project, when you start doing optimization, this type of tricks are perfectly legit. You can mess around with them and try to make your hardware simpler, and as a result, potentially faster or lower energy. Okay? So that was kind of the hint of the day. More to come. Is that clear? If you think about it, it's just pure simple single mode manipulation, but it's an important thing. We do this stuff a lot when you build high-performance hardware. Okay, that's the project. If there's no other general questions, issues to be raised, then we're going to leave the domain of arithmetic for a while. We'll come back, because I still want to do more complexities. I want to do multipliers, and I want to do some weird stuff. But for the time being, now I want to go back to logic. Okay? So we spent a lot of time so far on designing combinational logic circuits with CMOS. We found a set of ways of optimizing them, sizing them, and all those kind of things. We learned about logical effort as a way for us to sign complex logic block. Now, as I mentioned before, combinational CMOS, or complementary CMOS, is a great logic family in many aspects, but it also has some flaws. The great part is that it's robust, fairly easy to design, easy to automate, and all this type of things. And you don't have that many kind of nasty other things coming on the side. So it's a fairly straightforward logic style. However, it has one negative, a very important negative. If we look at complex logic gates, we see that its logical effort is kind of not that good. Compared to an inverter, you see that a 2-input NAND already has, 4/3 logical effort, and it goes up quite rapidly if I increase the fan-in. And why is that? Well, if you look at your CMOS gate, you have always this thing, right? Anytime I have a connection to an NMOS, I have a connection to a PMOS, which means that my load capacity, my input capacity, gets multiplied with a factor of 3. Okay? It would be nice to have a logic family where the input capacitance, the capacitance looking into the gate, is a lot smaller. If I don't have to connect to 2 transistors. Okay? So that's what we have been, that's all people have been trying to do in all those other logic families that they have invented over all those years, is trying to come up with logic families that have better logical efforts. Bottom line. So let me give you an example that you already know. Okay, we've done it in homeworks. You actually done it partially in the midterm as well. Yeah, you have done it in midterm. I said, well, I can build a logic family by putting a resistor and an inverter, and a NMOS transistor, sorry. It's a perfect inverter. It inverts. And as you can see from a input capacitance perspective, I don't see a PMOS anymore. I only see an NMOS transistor. Okay? Which makes me already believe that from a logical effort perspective, from a performance perspective, this is going to be a much better, or a better logical family. Okay? So what this thing does is, well, we say we make an inverter by creating a driver transistor and a load device. And the load device is there to pull up when the input device is off. We pull up the output to high, to VDD. When the input device is on, we pull the output low. But now you can see that in any one of those circumstances, you're always going to have a resistive divider. VOL is not going to be 0, but some number in between, right? And obviously, for noise margin perspective, I would like it to be as close as possible to ground. If you want to get nice noise margins, I would like to be VOL close to 0. So there's an interesting trade-off here. So you have your load resistance, and then you have your NMOS resistance. From a VOL perspective, I would like to make Rn as small as possible. Because remember, VOL over VDD is going to be equal to Rn over Rn plus RL. So if I make Rn small with respect to RL, VOL is going to be small. Right? So that's a requirement. I would like to have Rn smaller than Rp. But, well, I'll say one way of doing that is make RL very large. Right? I make a resistor of a megohm, of a gigohm, a teraohm, or something like that. But that comes with a catch as well. Because if you look at the transition times, you see that the high to low transition is going to be determined mostly by RL. Now, actually, the low to high is going to be completely determined by RL. The high to low is going to be mostly by Rn. Okay? So your different transitions, your propagation delay in the low to high and high to low are going to be dominated by one of those resistors. Now, if I make Rp, or this load resistance, very large, I'm going to be toast. Right? I basically have a huge resistance charging up your capacitor. Is going to take a long time. So you're losing the advantage of reduced logical effort because actually from the other side I will have a huge logical effort. So for the NMOS end, small resistor, small logical effort. From a PMOS side, or not the load side, sorry, not a PMOS, it's going to be huge. So that's not very nice. So we would like to have Rn very close to Rp from a performance perspective. And then there's the other catch. This logic family, or this class of logic families, will see when the output is low, the current to this chain of resistors is not going to be zero. It will have current flowing. This gate has static power consumption. Right? If you don't do anything, there's still going to be current flowing. So again, here for that, I would like to have Rn plus Rp as large as possible. If I make them very large, I will have less leakage current. But that might impact your performance. So there's a bunch of trade-offs that you have to play here. Do you care about static power dissipation? Do you care about noise margin? Do you care about performance? And that's the optimization game we're going to play here. Now, we call this logic family ratioed logic. And the main reason we call it ratioed logic is that in contrast to the CMOS inverter, if you take a CMOS inverter from a DC perspective, it doesn't matter what the sizes of the NMOS and the PMOSs are. I could have a gigantic PMOS and a very tiny NMOS, and still VOH is going to be VDD and VOL is going to be zero, independent of the size of the transistors. Here it's clear that VOL, the logical levels, are going to be a function of the ratios of the devices. Okay? So that's why we call it ratioed logic. Now, this is a simplistic vision. I could use a resistor. But a resistor, making a resistor is kind of, current day technology is not very good at making resistors. I could put a strip of diffusion or some polysilicon, undoped polysilicon or something like that. But getting the precise value on those things is very hard. Also, it's not the perfect load. Actually, there's better ways of doing this. So over the years, we've kind of gone to a number of different ways of implementing the load device. So instead of using a resistor, I could use a transistor as a load. But in this case, you can see that these resistors are not connected to the input. So the input capacitance I see is still only a single NMOS device. Okay? This thing only acts as kind of a load type of thing that helps us to determine where the logic levels are going to be sitting at. There's a couple of ways of doing this thing. One straightforward way was this. If I have only NMOS transistors, I could do this, right? I basically hear my input, this is my output, and I use an NMOS device with its gate connected to VDD as the load device. Okay? This is called the saturated load inverter. Now, again, it's kind of interesting. The name says a lot. It says saturated load inverter. Why would we say that? Why would you give a name like this to this particular gate? Sorry? That is correct. If you look at the top device, the NMOS device, VGS is equal to VGD. Right? The gate source is equal to the drain source. It's always equal because both of them are sitting at VDD. If you look at the equation, it means saturation. So if you look at the load curve of this device, so you have your NMOS device runs like this. The load curve of the NMOS device is going to be inverted here, and it's going to be sitting like that. Okay. So it's quadratic. It's a saturated load. If you put on the equations, you're always at the edge of saturation there, you will see that you get a quadratic kind of current dependency thing, if you don't assume velocity saturation. Now, this thing has one disadvantage. One major disadvantage actually is the position of this particular point here. When the input is 0, what do you get as output in this case? What's the high output of this device? Something we should know by now. Yeah, that's exactly right. We lose a threshold. Because you can see that this NMOS device is really good at pulling it up. Remember what he said before? NMOSs are very bad at passing a 1. So this thing will try to pull up the output node till it reaches VDD minus VT. At that time, basically the transistor shuts off. So the maximum value at the output is going to be VDD minus VTH. And if we basically have this thing connected to ground, you're also going to have body effect on it. So the VTH is actually going to be larger than the nominal value. Okay? So not a very good choice. So for a long time, people had actually, in the late 70s, when people were doing only NMOS design, like, you know, all your first microprocessors, actually the load they were using is a device like this. It's called a depletion load inverter. It's an NMOS device, but instead of getting the gate connected to VDD, you connect it to the source. Now you might say, gee, that's a really bad configuration, because VGS is always equal to 0. Thing is never going to turn on. The trick they used here was to use a device with a negative threshold. This is called a depletion load transistor. A depletion transistor is an NMOS transistor with a negative threshold, which you can do by doing some implants. I can move the thresholds up and down. So you can see that this acts as a current element, and actually was a fairly good load till, as I said, in early 80s when CMOS came in. There's another option, and this is probably the better option, is to use a PMOS load. And the PMOS load is you take a PMOS transistor and you connect the gate here to ground. Which means that in this case, the VGS of this device is always going to be equal to VDD. Okay? So we have here a device that, if I now would look at the current characteristics, this is my NMOS transistor. My PMOS load will look like something like a PMOS with a particular load factor, like this. Right, that's my PMOS device with VGS equal to VDD. Now you can imagine that if my output resistance is actually quite small, when the thing is flat, when you have no output resistance, when you have infinite output resistance, you can see that this thing will create a lot of gain. It almost looks like, in this region, the PMOS almost looks like a current source. Fixed amount of current pumping into the thing, which is nice, right? You get a lot of current, you start pulling down, and the current stays the same level while you're basically pulling down or up. So you actually get a lot of current out of this load device and actually gets some decent performance. So I think if all the logic families that are in the ratioed logic space, this is probably the most popular one. We call it pseudo NMOS because the PMOS load acts kind of like the good old NMOS days. It's like we did in the almost. It's kind of a nostalgia, trying to keep NMOS alive for a longer period of time. Yes, question?
Was there any mechanism for keeping it from like shorting out when you finally do get a 1?
Sorry, shorting out. Yeah, well, you have two dividers. It's a resistive load, right? It's the same thing. It's a divider. If I basically now have this transistor here, and you put VDD here, and this is grounded, same deal. You have two resistances. It's a resistive divider, and your VOL will be determined by the driving strength of the PMOS versus the NMOS. But again, you will definitely have, it's static current. Same problem. We haven't solved that static current problem, but we have made a somewhat better load than we did before. Good. So the idea with this is that if I look at this, suppose now I have to do a 10 input gate. In the CMOS gate, 10 inputs would be 20 transistors. Here I need only 11 transistors. 10 in the pull-down network, 1 in the load device. So 11, so it's a simpler gate, and potentially you can make it faster because of this logical effort type of thing I was talking about. So fast and basically simple, which is quite nice. But as I said, you pay some penalties in noise margin if you're not careful. Okay. So, oops. So here's an example of such a gate. We choose your NMOS devices, and you make your NMOS device, let's say, WY size. And you have to choose the size of the PMOS device in such a way that my resistivity divider as well, that my VOL is within the range I wanted to get it. Actually, it turns out that making them all the same size works actually quite nicely. Making the PMOS the same size as the NMOS works, because remember, the PMOS is always a weaker device. As a result of that, the resistance of the PMOS in this case is going to be larger, somewhat larger, but not much larger, about a factor of 2, than the resistance of the NMOS, because I make them the same size. And it turns out that it's a fairly decent ratio in terms of both for performance and in noise margin characteristics. Now, here's an interesting question, right? Remember, when I do CMOS logic, complementary CMOS logic, I do a lot of gates. What is the best choice of gate I would use? If I say I have to choose, I can use NAND gates, I can use NOR gates, I can use a mixture of the two. Which one would you prefer? Remember we discussed that in the past? It was NAND, right? NAND gates puts the serial devices in the NMOS network, while a NOR gates put the serial device in the PMOS network, which is always a pain in the neck. You have to make your transistor bigger, more capacitance, and so on and so forth. Now, if you look here, actually the situation is reversed. Right? If I do pseudo NMOS type of designs, actually it turns out that I don't want to have any serious devices. We don't have to worry about the PMOS network because it's always a single transistor. So from a overall logic perspective, it's clear that I would prefer NOR gates because I only get parallel devices, which is nice. No serial device, again, makes our speed faster. So you have to be very careful what you pick based on the logic choice you make. And as I mentioned, VOH is equal to VDD, and VOL depends on the PMOS to NMOS ratio. So here's some simulation. These are voltage transfer characteristics of some of the pseudo NMOS 2.5 volt logic. And you can see that depending upon the W, suppose I take a W over L of N, which is equal to 1, minimum size. Well, actually, it's not really. That's my minimum size device. And I make my PMOS quite strong. I basically make it W over L over 4. You can see that this is a pretty lousy voltage transfer characteristic. Noise margins will be sitting somewhere up. -1 might be God knows where, around here and here. So your noise margin is probably going to be sitting around there. And you can see that VOL is substantially above ground. Now, from the time I start making my PMOS smaller and smaller and smaller, your voltage transfer characteristic gets better. Like, for instance, if I make it 1/4 of the NMOS size, you see I get a fairly nice characteristic. But actually, you get also a very nice one already if I make W over L over equal to 1, same size of the NMOS device. I still get some VOL, but it's not very large. And that's why we chose this all transistors same size type of model. It gets you a decent voltage transfer characteristic. Okay, so what does it buy you? That's the question we're always asking ourselves these days, right? Now we have some mathematical techniques. We know about logical efforts. So it's always nice to say, okay, you propose a new logic family. Show me what logical effort is. Is it going to be better or is it going to be worse than what I can do with CMOS? Okay, so let's look at this logic family. And obviously, we have different behavior here in pull-up and pull-down mode. So we're going to have to compute logical effort for both different modes. So let's start looking first at a simple case, which is the low to high transition. Okay, in that case, this whole network is off. It's the PMOS pulling up. Okay? Now remember logical effort, we're looking at the input capacitance for the same driving force. Okay? So if you want to have a transistor or a gate, a CMOS inverter has the same driving force, and since you're using W here, we have to basically compare with an inverter which has W in the PMOS and W2 in the NMOS network. So the input capacitance of this thing is going to be 3/2/2. Right? It's 3/2. Okay, as we always did. So the W drops out. Now what do we see here? You look at the input, we see 1W. Right? That's what you see. If you look in here, the total capacitance is, it's 3W, is 1W. There's only one NMOS transistor connected. They have the same driving force, right? W in this case, W in this case, both of them are the pull-up networks. That's what we're looking at. So what's the logical effort of this gate for the low to high transition? Well, it's 1/3/2 is equal to 2/3. So effectively, this gate has a lower logical effort than a CMOS inverter. And that's exactly what we were hoping, right? Otherwise, we wouldn't have done it. Okay? So this shows again how you can use logical effort type of technique to compute how to compare various gate structures. Now that was easy. Now let's do the harder part. You've done this. It was part of the midterm. So you basically start knowing what's happening when I do things like this. When I have the high to low, the equivalent network looks like this. Right? Now, there's two different arguments to go on here. And I must say, I'm not siding with one or the other one. I'll present both. What is if you look at now, what is the driving force of this? How do I have to size the NMOS in such a way that I get the same driving force, let's say, of an inverter? Well, if you follow the switch approach that we have been advocating in class, what it says is that the driving resistance of this network is actually the parallel connection of RP and RN. Right? If I look at this equivalent logic network, this looks like a voltage source with a step, and then you have RP parallel RN, and you have a capacitor. Okay? So your driving strength is RP parallel RN. What this says is that if you take any large RP or some resistant RP and you put it in parallel with a resistant RN, the combined value is always going to be smaller than RN, which says this will be a fast gate. It actually reduces the resistance. That's cool. Right? Now, if you, however, look at the TPHL and you plot it for different values of the resistance. If I use, for instance, RP is equal to RN, you see that you pull down the output, and since they're the same, the V out is going to be 1/2 of VDD. Right? It's a resistor divider with both resistors the same, so it goes to 1/2. And then you have 2 times and so on and so forth, and you can easily describe this with this equation here. Now here's where the discussion comes. It's the definition of what's your propagation delay. Okay? Definition of the propagation delay is the 50% point. Right? Now some people interpret this at a 50% point between 0 and VDD. While the other one said, no. It's a 50% point between VOL and VOH. So it really depends on what I'm connecting here. If I connect this to a normal inverter, I might have to say, well, gee, for this thing to flip, I have to look at this 50% point between 0 and VDD. However, if I would connect this to another pseudo-array NMOS inverter, I think actually the more plausible argument is going to be the 50% point between VOH and VOL. Makes a big difference. Because if I look at the 50% point between VOH and VOL, I indeed get that answer. It says, hey, I'm going to be faster. It's RP parallel with RL. Because that's my time constant, right? My time constant is this RP plus RL. But you see there's another term which says actually our final value is not going to be 0, but it's going to be this intermediate value. If, however, I would look at the 50% point between 0 and VDD, you actually can see that actually making RP larger is a good idea. It makes you faster. If I actually make RP very small, or make them even equal, actually we'll never get to the 50% point. It's going to take an infinite amount of time. So we're going to get different values of the propagation delay depending on how we define the 50% point at the output. Okay? So both the arguments are right. And as I said, it really depends on what's the following gate. Is the following gate going to switch between 0 and VDD, or is it one that is also a ratio logic gate? Right? So that's important to remember. Okay? Now, if you take the other argument, it says, well, it's going to be between 0 and VDD. Actually, you can see that the reason it's slower, the thing that this gets slower and slower is the smaller I make RP, the more I take current away. I'm basically trying to pump current out of the capacitor, and this PMOS keep on pumping capacitor current back into it. So they're fighting each other. One tries to pull down, the other one tries to pull up. So what you get is two currents that you have to subtract from each other, and the resistance, the equivalent resistance, is not the parallel version, but actually is something of this nature. It's where you subtract resistances from each other. And you can see that when RP is equal to Rn, this is 1 minus 0, our drive becomes infinity, as we would show in the previous slide. So, bottom line is, both of them are right, but you have to be very careful on which one you're using, because the results can be very, very, very different. So let's assume that we take this one here for the time being. It's okay, we're going to assume that we're going to look at the output transition has to be between the 50% point between 0 and VDD. Okay, so we want to look at the logical effort in that case. So here you have your pseudo NMOS gate, and we're going to try to pull this thing down, and we look here as well. Capacitances, no change. We have 1W here, 3W in this case. Right? From a sizing perspective, in order to make this thing the same speed or the same driving force, remember now I'm going to use this equation, which is the equation I gave on the previous page, and I assume that RP is equal to 2 times Rn. Remember, they have the same size here, means that this one is double the resistance. This one here, you see that if I solve this equation, the one I just showed here, I put RP and Rn in there, you see that the equivalent resistance is 2 times Rn. Okay? So my driving resistance for the pull-down network is 2 times as bad as what I would get for the inverter. Okay? But at the same time, my capacitance is 3 times smaller. So what I get as the logical effort for the high to low, well, it's the same thing as before. We have a input capacitor, which is W, but we have to double it because we have half of the driving resistance is doubled. So it's 2 times W. For the inverter, we have 3 times W. It becomes, once again, 2/3, which is exactly the same as we had for the low to high transition. So in both cases, our logical effort is going to be 2/3, which shows that this gate, definitely from a performance perspective, is a good choice. Okay? But remember, static power dissipation. You're not going to use this for something which has 1 billion gates. If, however, there's a little circuit that you're really concerned about, it really has to be fast, throw a couple of those guys in there. It gets you some good performance and costs you some current, but that's okay if you only care about performance. Okay? Now, this just to wrap this up, this ratio logic, I've just shown some tricks that people have used to improve a little bit on this pseudo NMOS concept. Right? Remember, you're trying to trade off different things. Right? It's performance, noise margin, static power dissipation. Okay? During a transition, remember, during transition, I would like to have the PMOS as small as possible. Right? I'm going to transition from one to the other one. I want to have a small resistor there that's really going to be helpful for everything. However, from a noise margin perspective and a static power dissipation perspective, I would like to have the PMOS as small as possible, right? Large resistance, because then I get a very small VOL and very small power dissipation. Okay, so trade-off. So one argument says, why not combine the best of both worlds? Why not have both, a small PMOS and a large PMOS, and put them in parallel? So when I do a transition, when I basically have the logic switching, I enable that PMOS. Okay? Very small resistance, we're going to be fast, things are going to switch quite rapidly. And then when we're done, we turn off this device, and we have this for the static operation, when we're not doing anything, we put a very small, very large resistance, which basically means small power dissipation, which also means very small, larger noise margins, because my resistive divider gets a lot better. So by combining the two and having control signal, flipping one of the two on, I get a better device. Interesting trick. So this kind of starts introducing you in the art of clever design. This is what people do. Come up, I have another transistor there, and do a trick. Suddenly I get something a little bit better. Okay? Hopefully. Not always. Here's another version of this thing. It's the same idea, but somewhat different. It's something that was invented by IBM years ago. Some people call it DCVSL, and I'm trying to remember. Differential cascode voltage switch logic, if you want to know. It's differential. It's there's a cascode device, there's a voltage switch, and it's logic. Now, what this does is the following thing. It's here's the idea. Suppose I have available at my inputs not only my normal inputs, but also the inverted values. The inputs are complementary. When I have A, I have A bar. When I have B, I have B bar. That's why we call it differential. You have always from every single, the single and the single invert. Okay? This structure here, we know. If I would ground this is a pseudo NMOS inverter. Logic network and a PMOS network grounded on the top. This network is the same. But instead of grounding this, what we're going to do is cross-couple them. This is the first example of feedback we're seeing in this lecture, in this class. There's actually, you can see that there's a feedback network somewhere hidden in here. One of them feeding back to the other one and going in a loop. Feedback will become very important when you start talking about registers. Okay? The other thing to remember is that this is F. This network is the complementary network. So if this network F implements AB, the other network we're going to implement AB bar. Okay? So they're basically complementary to each other. And I'll show you examples of how this exactly works. Okay? But remember, I have always A and A bar available. That's going to help me a lot to this complementary type of networks. Both of them are NMOS networks. Now, the beauty of those complementary networks is that at any time, depending upon the inputs, one are going to be enabled, the other one is going to be off. Right? Since they're complementary, they never can be high at the same time. Or they never can be enabled at the same time. So suppose I imply, let's say this is at 1, this output is at 0. Okay? That's the initial condition. This thing's sitting there. Now I apply a set of inputs that suddenly enables F. Okay? This input is at 0, means this PMOS is on, pulling this node up high. Right? That's the conditions here. This node is 1, this PMOS is off. Now suddenly I start pulling here. I turn this network F on. I start pulling down that node. It's fighting against the PMOS. The PMOS is still on. Right? The PMOS, and they have this NMOS network trying to pull it down, just like we had in pseudo NMOS. Okay? So we're starting to pull this down, but by doing so, while this starts to pull down, we start actually slowly but surely turning on this PMOS. Okay? That's the feedback effort. We bring this down, the PMOS, this PMOS is going to go off. We start pulling those nodes up high. Slowly but surely we're turning off this PMOS. And suddenly this goes high and the whole thing flips around from one side to the other side. Okay? So the beauty of this network is that this network doesn't have static power dissipation. By using the feedback, look at this. When this is, let me just clear this out again. let's look at the condition 1 here, condition 0 here. This is 1, means that this is off, this is on. 1 means that this network is off, not pulling down, this network is enabled. So you see that when the NMOS network is enabled, the PMOS transistor is off. When the NMOS network is off, the PMOS transistor is on. So you get kind of complementary nature between the two. We don't have the same thing that happened in ratio CMOS. By adding that feedback, we can actually turn off the load at the end of the action, which is really the beauty of this thing. This thing doesn't have static power dissipation. It has a lot of weird things happening in it. Obviously, you have that feedback thing. You have to first fight feedback, always going to try to prohibit you from doing something for a while. But when you can convince it that it should move, and you have to work hard on that, suddenly it moves really quickly because you have that feedback loop really amplifying the thing, and the thing is going to go from one state to the other state almost in no time. So very sharp transitions from one state to another state. Okay? So this is called differential cascade switch logic. Let me show you an example. But here's the, just to show you the waveform to explain exactly what's happening. So we have AB here, and they're switching at the same time. That's AB bar. You can see that I'm starting to pull down initially one node. Remember that node, I turn that NMOS network on, and I'm starting to pull that node down. And it's hard. The system is resisting me. And the other node doesn't do initially anything. But when I get to a certain point, I start turning on that other device. This node starts to go up, and then suddenly it switches and it goes really fast here. So this is an example of that feedback action that you have to overcome. When you overcome it, it goes quickly. Okay. So let's do an example here. So I have a device, and I would like to design an AND gate, something that it does F equals A and B. Okay. In order to have a pull-down network that does AB, I have to have the network and the network invert. So I have to have the second function is AB bar, and that's going to be A bar plus B bar. So if I now do this, right, is have in one network AB, the function I'm going to get here is AB, or this output is going to be AB bar, obviously because it's inverting. On the other side, I put two NMOSes in parallel, and have A bar here, B bar here, connect them to this PMOS transistors, another PMOS transistor, and I cross-connect them, and we're done. And this is AB. This is why I need the single and single invert available to me, because that way I make my logic network a lot simpler. But you notice also that any one of my gates always produces single and single invert as well. Right? So I always get both polarities available anyhow, because that's the way this gate works. And it turns out, and you might say, well, gee, this is more complex, right? Now, instead of having one function f, I have two. So this is going to hurt me to a certain extent, because I look like the whole thing is going to get bigger. And obviously, this is a little bit more complex. Maybe the whole thing is going to be slower, too. But there's one thing you have to remember. Suppose I do a large logic block, and I want to implement some very complex function, g. Okay? To implement g, if I have only inverting logic available, I remember inverting logic, CMOS is only inverting. Sometimes I will have to do special tricks to get the right polarity. I have to put inverters in between and all those kind of things to get the right signals. Here you don't have to do that. You always have single and single invert available to you. So people have shown that you take an ALU, fairly complex ALU. So you look at how many gates you have to put in sequence between input and output to get the function. And then you do the differential implementation. You see that the differential implementation typically has about 50, 60, 70% less logic depth. Because of the fact that you don't have to have these extra inversions, your logic is easier to implement. Very good example. This is the most nasty gate of all of them. XORs are always a pain. you have to do CMOS XORs, it's really painful to do so. Here an XOR is a quite simple function. And actually you can even be cleverer. What this thing has done is actually make sure that you can implement F and F bar totally separately. You say, well, maybe occasionally I can share some transistor between the two. This one actually shares, those A and A bar transistors are shared between the two networks. And then the B's connect to the different outputs. So I can get away in XOR here with 6 transistors in the pull-down network and 2 in the pull-up network. Okay? And again, those guys can be fairly minimal size. They don't really have to be very big. So interesting logic family. And as I said, basically same concept as ratioed logic, but it doesn't have the ratios anymore, and it doesn't have the static power dissipation anymore. Okay? All right, that's that. Now, interesting logic family, limited usage. I said the static power dissipation becomes an issue. And you can also imagine if I have to do differential logic, that's going to cost me a nightmare from a wiring perspective. You double the number of wires. Otherwise I have A, B, C. Now I have A bar, B bar, C bar. They all have to wire and connect. You get a rat's nest, and typically it pushes the logic a little bit apart. Okay? All right. Let's go to something different. New logic family. Pass-transistor logic. PTL. Logic family that's, again, this is a niche logic family. Not something you're going to use for every possible design. But for certain things, it is darn good. You go to our friends at Xilinx or Altera, the guys basically making programmable logic, FPGAs, they will tell you that they love pass-transistor logic. It's the easiest way to make programmable logic. And most of the stuff they're doing is all based on pass-transistors. Okay? That might become clear later why, but let's look a little bit at what the idea is. Okay. Let's go back to lecture number 1, right? Or lecture number 2. Remember how we decided to talk about logic? How do you do logic? Well, it's switches, right? And how do you do logic with switches? Well, you put switches in parallel and you put switches in series. Right? That's the way logic works. So I could do a variety of, I can do any logic function by putting switches in sequence. Like we would do with relays, mechanical switches, and so on and so forth. Same deal. Like for instance, I claim that if I have 2 switches here, one of them is A controlled by B, so this implements the function A, B. And this is B controlled by B bar that implements the function B, B bar is equal to 1. 0, sorry. Now, why would I have only AB? Is that this is an AND gate, right? So it sounds like a good idea. Now, why in the world would I ever put a second transistor here? Right? Seems like a crazy thing to do, to put 2 transistors in sequence that implement a function 0. Right? That's actually a dumb thing to do. Now, before I explain that, let me explain first some properties of pass-transistor logic. So what we're going to do is build complex logic networks using only switches. Occasionally, I'm going to put an inverter in between, a buffer. Because if I have only switches, you never connect to VDD and ground. Right? There's logic, 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 logic. You never connect to VDD and ground. If you don't connect to VDD and ground, to what I get is something that's not regenerative. There's no way I can get gain, right? If I have a sequence of switches and I inject noise on one side, noise will happily propagate and keep on adding. So switches themselves are not regenerative. So occasionally you throw an inverter in there, and the inverter pulls it back up to VDD and ground, and bingo, everything is cleared out again. Right? So collection of switches. But as I said, there's an issue. If I would implement an AND gate like this, A, B, what can we say about this output node here? When B is low, it's not connected to anything. It's floating. So you hope that your capacitor can store your value, but this definitely is not going to be a 0. It might be wrong. It might be storing the previous value. It's a memory. So it's not going to implement your logic functions correctly. Also, this is clearly not static logic. Remember static logic? Always a path to VDD or ground at any point in time. So this would be becoming dynamic logic, which we're going to talk about later. So what this BB bar does, it says when B is high, then obviously we get A at the output, which could be a 0, could be a 1. That's cool. The output is always defined. Now what's happening when B is low? Well, it's AB function. When B is low, we know that the output should be 0. So we close this switch, and basically depending on the value of B, we basically always get a 0 here. And because the B bar is high, switch closes, and B is low, we get a 0 at the output. So this ensures that under all conditions, our truth table is either a 0 or a 1. This implements the 1. If you look at the truth table, you have A, B, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. So this is implemented by AB. When B is high, this is also defined. And this BB bar combination implements those two lines of the truth table and ensures that we're always going to get a 0 there. Okay? Because B bar is low at this particular point in time. Okay. So that's the idea. Same thing. I could do BB bar. If you're for a little bit more adventurous, I could also connect this to ground. Same deal. Doesn't matter. Same function. But you can see this is a very simple logic implementation. I can do logic networks by putting these things together and chain them together over quite a bit of stages. Now, there's one challenge. And again, it's a challenge you already know. You've seen it before. Same problem. If I use this network, what can we say about this node again? Second observation on this node. Now, I know it's always defined, but there's another challenge. Yes?
Never gets up to VDD.
It never gets up to VDD. That's right. You get a threshold loss. Because this is only NMOS transistors. And if I want to pass, if this is 1 and this is 1, I'm going to get VDD minus VTH here. So who cares, you know, a little bit of a VTH loss. Actually, it's reduced swing, it's less power, so it's actually a good feature. Well, yes and no. It has some challenges, right? Number one, if you look at pulling up a node all the way to VDD minus VTH, you see this NMOS device really towards the end, when it gets close to VTH, it gets very little current. It's extremely soft. So getting up higher is really going to take forever. That's one thing. The second thing is that you have to be aware that I'm going to put this in an inverter, okay, to create regeneration. Now, when you get a 0 here, this is 1. That's cool. However, when I apply VDD minus VTH here, you have a problem. Because we don't get VDD, we get something which is lower than VDD. Our PMOS will, as a result of that, you'd like to have the PMOS here when you want to have a 0 here, when you want to get a 1, get a 1 here, a 0 here, you want to get the PMOS to be as off as possible. Otherwise, I get leakage current to the inverter. Now here, suppose, for instance, that the NMOS and PMOS have approximately the same threshold. Means that when this is VDD minus VTH, it means that my PMOS is going to be on the edge of conduction. Right? We're just applying an input voltage. VGS is going to be equal to VT. So that would already be bad, because you know that there's already a substantial amount of current flowing. But it's worse, because remember, this is VTH at VDD. Body effect plays. This threshold drop is going to be larger than the NMOS VTH, but actually the NMOS VTH adjusted for the body effect. And as a result, this PMOS device is not only going to be at the edge of on, but actually it's going to be actually on. And this becomes a leaking device, pretty badly leaking device. So that's a challenge. That's the big problem with NMOS only networks. Definitely, if you follow it with this inverter type of reconstruction logic. And this simulation just shows you that exactly. As you can see, my input goes up. My node X kind of lumbers upwards and gets to VDD minus VTH. The output after the inverter follows very nicely. Right? Once this goes up, once I get basically to the 50% point here, this output will start dropping quite nicely, so that's cool. Very nice characteristic. But you see at the end, the VGS of my PMOS device is going to be, in this case, actually more than 1 volt. Not a very happy situation. That thing is going to leak like a sieve. Okay. Like always, I said, that's cool. Well, it's not cool, but we have to do something about it. Right? What are the tricks we can play? And give it to designers. They're always going to find a way out. Right? Okay, I already explained that. Here's approach number 1. Looks complicated, but it is not. It's called a level. We're going to add one more transistor to it. So you have your complex NMOS network with all your switches in sequence, and then you have this buffer, this inverter. And what I'm going to do is add one more transistor in here. It's a PMOS device. And as I said, we call it a level restoring device, or very often also called a bleeding transistor. Okay? So what does this do? Think about it. So when this is low, and this is high, this is low, this is 1, you can see that the VGS of this PMOS is going to be equal to 0. PMOS is off, doesn't do anything. Okay? So that's fine. We're in good shape. Everything is normal, right? We have all normal values and so on and so forth. What we're really concerned about is the other situation. Okay? When I now apply a 1 here, okay, this is going to go up to VDD minus VTH. What's going to happen as a result of that is that this inverter is going to switch and this 1 is going to go to 0. Which means that we turn on the PMOS here. PMOS gets turned on. And as a result of that, instead of going to VDD minus VTH, when the NMOS dies, because the NMOS works hard, get to VDD minus VTH, but before it dies, actually at that point in time, this PMOS gets in action and takes over the job of pulling it all the way up to VDD. So it's, you're done your job, you switch the gate, now I'm going to pull the output node or this intermediate node all the way up to VDD. Now as you can see, this is again a very nice example of a feedback loop. We have a feedback loop in here. We feedback the output signal towards some of the intermediate nodes. So to get full swing, right? So that's a kind of nice thing, a very popular design strategy. A lot of designs will use exactly this approach. The little feedback loop, bingo, node goes all the way up, we're done, all problems are solved. However, 2 challenges, right? You have to be aware that this restoring device is going to make things not as good anymore as it used to be. Because right here, if you look at this node, right now has a diffusion of the NMOS device, diffusion cap of the NMOS, has some gate source capacitance, and then the gate capacitance of the inverter that follows it. Now we add another diffusion capacitance to it. Okay, other diffusion capacitance plus some more gate source capacitance. So we increase the capacitance of the node to a certain extent. It's going to make it a little bit slower. Probably will impact logical effort. We expect it to do so, because larger capacitance typically doesn't bode very well in general. There's another problem you have to be very careful about. You have to be very careful with the sizing of this transistor. Suppose I make this transistor, this one here, very large. So okay, I'm going to do a really good restoring job. I make it a real big transistor, very wide. Now you have this poor NMOS device here, minimum size, is trying to, so this is 1. If you look, let me again clear it up. Suppose here now we're in 1 mode. This transistor is on, right? So the output is 0, PMOS transistor is turned on, big force. Now we're going to try to put a 0 here, so this is 1. We try to pull this node low. Okay, we put a 0, we would like to make the gate to switch. So again, what you see here is a device that has temporarily something like this. So this is my NMOS, this is my MR. This is equal to 1. I have an NMOS device that tries to pull down this node. But if this device is really big, it's a ratio, this looks like what? It's a pseudo NMOS inverter. And remember about the VOL? Depending upon the ratio of those transistors here, the VOL will be positioned at a certain place. If the VOL will be larger than the switching threshold of the inverter that follows, you're never going to switch the gate. It's something, that gate is stuck. There's no way in the world, whatever I apply at the input, I can pull low and keep on pulling, it's not going to go anywhere. The output is going to stay low. I'm stuck. So obviously the message here is very simple. This guy, the reason we have this restoring device is the only reason we have it there is to make sure that we can go to pull it up to VDD. So make it weak. Make it weak compared to the NMOS network. And if you do so, then you don't have any problem because the weak device has small capacitance. That's nice. And it allows us to switch very nicely in both directions. So you have to be aware of that. It takes some challenge. So this is an example, for instance. This is an example, for instance, of a very large restoring device. And you can see I'm trying to pull down to 0, and the thing starts and never goes anywhere. Stuck. While if I make the device weaker and weaker and weaker, we get much better characteristic, and we can pull it all the way down. And here you see the fighting action. You see a curve that doesn't go down kind of in a very nice continuous fashion, but kind of has a slope like this and then like that. That's where transistors are fighting with each other, and suddenly somebody wins and takes over, and the slope changes. Okay? All right. Let me say a couple of things about logical effort. Like as I said, this is our tool of favor now. I'm going to use it over and over again to figure out, hey, is something good or something bad. Now I'm going to ask you the question, here's this gate, which is an AND gate, right? What's the logical effort of this thing? Okay? And if you start looking at it and say, boy, that's hard. I don't even know where to start. Because remember, logical effort is you look at the input capacitance, assuming that you have the same driving strength. So now we have to figure out what is the driving strength of this thing. That's pretty tough to figure out. Okay? Because if you look at, let's say, input A, when you look at input A, we have to compare how fast this thing would basically work. Well, we have a resistance here, but what's the resistance that we're sitting at the A side? It's kind of very hard to figure this out. I cannot, for myself, figure out what if I would like to solve the RC time constant of this, I don't know really where to start. Why is that? Because of the fact there's no connection to VDD and ground here at the input. So if you want to do this correctly, you have to actually extend the question a little bit. Actually, the more realistic situation would be something like this, where A comes out an inverter, a restorer, and then we feed it into the network, and we have a BNB bar network. Because now, for my overall computation, remember, inverter has basically equal to a resistance which is equal to Rn, and has a capacitor which is 3 times W, right? That's the reference case. So we look at the gate capacitor that we see for A bar. Let's look at the input A bar in this case. Well, the gate capacitor is what? The same as an inverter, right? 3W. What is the resistance that we see between input and output? Well, we have a PMOS and an NMOS in series, in both directions. In the other case, when we go down, it's NMOS and NMOS. Okay? So what means is that the resistance, both of them have the same resistance, Berkeley 1. So actually the resistance is going to be equal to 2R. Or in other words, the logical effort for this thing is going to be 2. Okay? So if you take that driving device into account, you say, hey, this ain't good, right? Because this is a gate that has logical effort which is worse than what an inverter would give me. It's already well, it's not that bad because it's actually implementing an AND gate. So it's already, an AND gate has logical effort, which will be 4/3. So, you know, but still, it's not something to be perfectly happy about. However, look at the other guy. We've done that. Look at the other guy. If you now look at the B input, okay? Look at the B input. there my capacitance is going to be equal to 1 W. Right? That's what I see here, is a single transistor. Resistance, same thing, is 2R. Okay? So I look at the logical effort. My resistance has gone up with a factor of 2, but my capacitance has gone down with a factor of 3, so I get a logical effort which is equal to 2/3. Okay? So I win. From the B input perspective, I'm better than the inverter. From the A input inverter, I'm actually worse. Okay? Which shows that this is a fairly asymmetrical gate. Fortunately, you will see that a lot of the inputs, we're basically, if you use this logic family, we're very rarely going to connect through this side here. Definitely in, let's say, FPGAs, all the logic, all the inputs are always going to be at the gates of the transistors, and those things are going to be fixed values. I'll come back to that next lecture, show you what you can do with this type of thing to build, let's say, an FPGA type of device. So they use that feature to make very simple logic gates, small logical effort, very small number of transistors. So that's really where pass-transistor logical effort plays it. You can do the effort, and as a little homework, try to figure out what's happening with logical effort if I add, let's say, a little tiny little PMOS device here for a level restorer. Okay. So what we're going to do next lecture, I'm going to show you just some examples of pass-transistor logic, and then we're going to start doing dynamic logic. That's for the real macho guys that really want to get very high performance. That's when you do dynamic. Okay? Oh, by the way, one issue, there's a couple of people have mailed me because they couldn't find a partner yet for the project. If you haven't gotten a partner, send me an email, and I'll see what I can do, basically connecting people up and so on forth. Okay?